Okay, let's start. So I'm Chen Ling. So I from Quasar Technology. I based in Shenzhen. So today I will talk about the recent works with using deep learning techniques to solving the cocktail party problem. Before that, I first will introduce what is cocktail party problem. So as we know, we are in a party. So we there are many people. We talk to our friends. But we still can hear our friend's voice. Then we overlook others talk, or we overlook the background music. So we only focus our attention to our friend's voice. So we call this is the cocktail party effect. So the Professor E.C. Cherry do the experiment to show the effect. But now no machines has been conducted to do such kind of things just like human. So in this work, in this talk, we would like to introduce us the recent progress in speech separation or speech extraction to solve the cocktail party problem. So we would like to formulate the cocktail party event in such kind of these figures. So we have the talk voice will be directly into the sound. Will be directly captured by the microphones. Also the voice will be reflected from the words. This reflection sound will also be captured by the microphone. So this is the vibration. We also have some other talks. We call this is the interference speakers. We may also have some other noise, for example, the air cons or the other background noise. Sometimes we also have different kind of microphones, so they may have the channel distortions. So if we because due to the COVID-19, most of the time we are doing the online conference or the real-time communication. So we also has another scenario which is echo. So we also have the echo cancellation. So for different kind of scenarios, we may have different techniques. For example, if we only get the speech, we want to remove the noise, we have the speech enhancement. So the speech enhancement will remain all the speech of different talks. So we also have the speech dereverberation, which is we remove the reverberation from the reflections. We also have the speech separation, which is the main topic of this talk. We are going to separate the speech of each talk into an individual channels. So before we start to introduce the techniques, we would like to talk about some background of the speech separation. So speech separation aims to let machines have the same auditory ability as a human in a cocktail party environment.
She has no idea whether it's Russia, China, or anybody else. She has no idea.
So we have so speech separation. What speech separation?
Whether it's Russia.
Sorry, it's automatically plays the video. So speech separation try to recover all the original speeches of each talk. Then the separated speech will be in individual channels. So for example, we have this debate.
She has no idea whether it's Russia. She has no idea whether it's Russia, China, or anybody else.
I am not quoting myself. I am quoting
Hillary, you have no idea.
17 do you doubt 17
our
military
country has
and
no idea.
civilian agencies? Well,
yeah,
he'd rather believe Vladimir Putin.
So this is an old demo which was done by me in 2017, I remember. So we have the debate of Trump and Hillary as well as the video. Actually, we check the speech part. Then we do the separation. We try to separate the speech of each one. Here is the result of Trumper's voice.
She has no idea whether it's Russia, China, or anybody else. She has no idea. Hillary, you have no idea. Our country has no idea. Yeah, I doubt it. I doubt it.
So here is the separated voice of Hillary.
I think it's time you take a stand, because I am not quoting myself. I am quoting 17 do you doubt 17 military and civilian agencies? Well, he'd rather believe Vladimir Putin.
So let's back to listen to the video again.
I think it's time.
She has no idea.
So here we can see there is some interrupted speech by the anchors. So we remember this because we are also hear the interrupted speech in the Hillary's channel, right? So we will talk about this later.
She has no idea whether it's Russia, China.
Sorry. So for speech separation, we divide it into the multi-channel and the single-channel one. For multi-channel, we have an additional information which is spatial. We have the angles of where the source comes from. So with this information, we can improve the performance by forming our beam to the target to the source. So for the single channel, which means we only have one channel of mixture recorded speech. So with this speech, we don't have the spatial information, which is the direction of each of the top. So we can the information we can use is only the signal itself. So for the single channel method, we are trying to using the recorded signal as input to do the separation to get the estimated speech of each of the speaker in the mixture. So, so as we say, why do we need to do the speech separation? Actually, for many real-world applications, we need to do speech separation. For example, human-machine interactions. For example, we have the robotics in the shopping mall. There are a lot of noise. Also, maybe some interference speaks voice are being recorded. So also for the hearing aids, for the teleconference smart device. So if we don't solve the problems to handle the multi-talk scenario, then this the usage of these real applications will be limited. So here I will briefly introduce the history of speech separations works. Actually, speech separation has been studied for many years from the auditory models, which we call the computational auditory scene analysis. They use the pitch continuity, vocal continuity, temporal continuity, harmonics, common onset or offset. So they use these information to do the separation. After that, we have the decomposition models, which is the signal processing based method, for example, the ICA, AMF series. After that, we have the statistic models, which is the GMM. In recent years, we moved to the deep learning. Actually, today we mainly focus on the deep learning techniques to solve to do the speech separation. So here is the performance of the recent works on Wall Street Journal to mixture database. So you can see from 2016, we achieved 10.8 SDI improvement. So SDI means signal to distortion ratio. Until now, we can achieve 22.4 dB improvement. So today, we mainly focus on this kind of techniques. So for speech separation, we mainly actually here we show source separation. Actually, source separation including several categories. The most important one is the speech separation. So source includes a lot of signals. So if different kind of signals combined together, we can divide them into each individual channels. So we say the speech separation means we separate the speech of two talks, which is a hard, actually is a hard task. So we divide the speech separation into frequency domain and time domain. What means by frequency domain, time domain? Frequency domain means we do the short time Fourier transform to get the magnitude and the phase spectrogram. So for the time domain, that means we use the signal itself as the input to do the end-to-end learning. So before that, we will introduce a concept which is auditory masking. So human has the masking effect, which is we only if the signal of is lower, the energy of the signal is lower than another one, so we can only hear these higher energy signals. We cannot hear the lower energy one. So here is the in the frequency axis. If we call this as the simultaneous masking. So for the temporal dimension, we also have this masking effect, which is the temporal masking. So with this masking effect of human, so how can we invent a mask which is to filter the voice of others only to focus on one of them? So we developed the ideal binary mask, which is we giving a value to each of the time frequency being either 0 or 2 or 1. So this is a hard mask, either 0 or 1. So here is the performance. Here we use the ideal binary mask. So here is if we use this ideal binary mask, so here is how is the performance of the separation.
Bismarck serves as a trade and shipping point for an area of large mechanized farms.
So we can hear some interface, which is da da da. Actually, because this is the hard mask, which is either 0 or 1. To improve the quality of the signal, we invent the ideal ratio mask, which is a softer one. For each time frequency, we have a value which is between 0 and 1. So we have this. Let's hear the voice.
Bismarck serves as a trade and shipping point for an area of large mechanized farms.
So here you can see the quality of the signal is much slightly better. So we also have some other masks. If you are interested, you can see this paper. They actually summarize several different masks. So for the frequency domain speech separation, previous works mainly focus on the form the separation into 3 different categories, which is we direct spectrogram estimation, which means we do the feature mapping using a neural network with a regression task. It means we have the signals in, we do the short-time Fourier transform, we get the magnitude spectrogram and the phase spectrogram. Then we do the neural networks to estimate the spectrogram of each talk. Then we have the clean magnitude spectrum of each talk as a reference. We calculate the errors between the estimated and the clean one. So we do this feature mapping. Another one is we do the mask estimation, because previously we have calculated the ideal binary mask and the ideal ratio mask according to the clean speech. So we can use that as the reference to estimate the mask directly. After we estimate the mask, we can use the mask to filter the magnitude of the original mixture signals. So we can use then we can get the estimated magnitude spectrum of each talk. Then we can use the phase of the original one to reconstruct the signal. So the direct signal estimation, what what that mean? It means because first we use the ideal binary mask or ideal ratio mask as a reference. Because this mask is not optimal, so it does not estimate the signal itself. So we want to estimate the signal by using a masking inside, which is we have a layer to estimate the mask. The value is contained between 0 and 1. So we call this as a mask. Then we calculate, we filter the magnetic spectrum by this mask, and we get the estimated spectrogram. Then we use this spectrogram to do to calculate calculate the errors to train the neural network instead of using the mask. So this three methods we call is the traditional one or the conventional one because they don't solve the permutation problem. What is permutation problem? It means we have several outputs, right? Then we have several reference. So how can we calculate how do we assign the reference to the estimated one to calculate the errors? So in this method, they just using the fixed assignment, which is estimated one is calculated with output one is is calculating the error with reference one. Output two is calculate the error between with reference two. So they don't calculate the permutations. So this work doesn't generalize real to unseen speakers. So after that, recent works mainly focused on to solve the permutation problems, which is using the analytic continuity, using the deep clustering k-means of speaker IDs to form the center of the speaker. Also, you have the permutation inverse training. Have the two-stage one. The first stage is to do the frame level separation. Then the second stage is try to grouping the frames of each separated speaker. So another one is a fixed level assignment in permutation inverse training. So later I will introduce all of these kind of works. Another work try to solve is to do the phase estimation, because in the frequency domain we have the magnetic spectrogram and the phase. When we reconstruct the signals, we always using the phase of the mixture signal. So this kind of phase is not optimal. So we have the phase sensitive mask. We have the unfold iterative phase reconstruction. Also, we have the most of work you doing the time domain method to avoid the phase decomposition. Another one is vocoder, which we have learned the mere features. Then we can use the vocoder to reconstruct the mere features into the time domain signals. So another problem need to be solved is unknown number of speakers problem, because during training we always know how many speakers in the mixture. Then we have the equal number of outputs. But for the inference, because we don't have the prior information, we don't know how many speakers in the mixture. So if we train with a fixed number of outputs, then we cannot handle the mixtures when the number of speakers is larger than the number of outputs we have. So another work is we try to use the PID. Actually, we can train. One of the solutions is we can train as many as outputs as possible. So in that case, we can handle some of the case. Another one is we do the iterative separation. It means we separate one speak at one iteration. Also the speaker ejection, which means we only focus on the ejection of the target speak by giving a reference clue. So now let's talk about some representative works. For example, the deep clustering. The deep clustering try to learn unbending for each time frequency spins. After that, we can use this to estimate affinity matrix. As we know, we have the clean speakers. Then with the clean speakers, we can calculate the one-hot speaker labels for each of the time frequency spins. So we also can get the ideal affinity matrix. So we calculate the errors between the ideal and the estimated one. Then we can train the network to learn the unbendings. After that, after the training, when we do the inference, we can use the k-means to cluster the unbendings together. For example, one speaker's unbending, we cluster them together, then we form a mask. Then we use these masks to filter the spectrogram of the mixture species. So after that, there is DC++, which is to incorporate the enhancement network after the mask estimation with soft masking. So it means it can conduct the end-to-end training of unbending and clustering together. Another work is to try to use the ideal mask or KB to form an attractor. This attractor is like a center of the speaker. So we use this center as one of the information we can get the speech of this speaker. Then use this information. Use the attracted speech. We can calculate the loss, and then we can train this network. As we progress to show that the conventional regression method or the masking estimation method, they're using the neural network to estimate the output directly without doing some speaker centering or the clustering. So this work tries to improve the traditional one by solve the permutation problem with permutation invariant training, which is calculate the loss across all the permutations, then get the minimal one. With these minimal errors, we use this permutation to assign the labels to train this network. So this network, this work using the feedforward and the convolutional neural networks, they cannot capture the sequential information. So the input is a context of the windows. There is a problem is the permutation may be switched across the context window. So they further proposed the bidirectional LSTM as a network to learn the sequential information to force the output of this one is belonging to a single speaker. So the same permutation invariant training is calculated. Because here we still calculate the loss frame by frame to get the final by sum them together to get the final loss. So without consider the context information. So after that we consider to propose a constrained permutation invariant training, which is we consider a context of the output to calculate the errors between the reference one and the estimated one. So in this case, we can have the context information to force the context windows to be continuity. With the bidirectional LSTM and the gradient LSTM to learn the features, then we can capture the long sequential information. So so the output of the speech of each speaker will be improved. After that, we also propose to using a multitask learning, which is we use the information of labels to show what categories of each time frequency belonging to. For example, for this each time for bin, we have 3 categories. Here it's the silence. Here is a single speak. Here is the overlapped speech. So we use the softmax to classify whether this time for bin is belonging to one of the 3. So we use this multitask learning to further improve the performance and explicitly to tell the network how to estimate mask. For example, for the silence part, we can give in a small value of just a 0 as the mask. For the single one, we can give in 1 or approach to 1. For the overlapped part, we give in the mask between 0 and 1. So it can help the network to learn the mask. Until this work, we only focus on the improvement of magnetic spectrogram. So even though in this PIT method, we use the phase-sensitive mask to compensate the phase difference between the mixture speech and the clean speech, but it is still not as good as the clean and phase. So in this work, it proposed multiple iteration phase reconstruction method. As we know, we have the separation of each speakers. So we have the mixture speech. We use the phase of the mixture speech to reconstruct the signal. Then we sum all of the separate speech together. Then we get the errors between the input and the sum of the estimated one. We get the error. Then we divide the error by the number of speakers. Then we compensate each of the output with these errors. Then we do the short-time Fourier transform again to get the refined phase information. Then we do the signal reconstruction again. Then we get the signal. So we do the several rounds. Then we finally can improve the performance. But then here has a problem is we in this case we only can handle the mixture is only contains the speech of multi-talks without noise and vibration. If noise and vibration is occur in the mixture, then this method cannot be worked. So this is so why we in the following work, so we want to use the time domain to do the end-to-end modeling. So also in the programming domain, it has a 2-stage method, which is we do the separation first, then we do the second round grouping. This grouping is try to clustering the frames of the same speaker together. So so with this 2 stages, then the performance can be improved. So when we evaluate on the work situation to make a database, then we can see the 2-stage mesh that actually achieves significantly better performance. So if we do the multi-run in the phase reconstruction, then we also can improve the performance. So here, if we do the constraint, which is we use the context in the loss function, we can further improve it compared with this one. So this is the deep clustering method, which is different from the method to do the direct mask estimation. So in this work, so we also define error to show how is the separation quality of our system. Because previously we just see the signal to distortion ratios, but these numbers cannot show some case, which is we cannot know is this separate speech has other speakers voice, which is we call the insertion error. Here corresponding to a deletion error. Also, sometimes is a substitution error. So we calculate this frame leakage error rate, which is similar to the word error rate. in the speech recognition. So with this, we can know that with the context inside the loss function, we can significantly improve the performance to reduce the deletion, insertion, and substitution errors. So actually, in many real applications, for example, our online conference applications, we don't tolerate the deletion errors. It means the speech of the speaker's voice is missing. Then others cannot listen what he's talking about. This is cannot be tolerated. So we also call this is the oversuppression problem. So with this FLER, we can have the individual deletion error, insertion error, and the substitution error. Then we can evaluate how is the performance of our system to set a threshold to our real applications. So also we do subjective evaluation because sometimes when we see the SDR is better, but the perception quality may be not as good as the lower SDR systems. So with the listening test, we can see the proposed system is better than the baseline. So here is some examples of the comparison between the baseline and the proposed system.
Bismarck serves as a trade and shipping point for an area
so
of
we can see one of the
mechanized farms.
speaker's voices still remains in the output set in the output. So there are many insertion errors.
Bismarck serves as a trade and shipping point for an area of large mechanized farms.
The insertion errors is reduced significantly. So here is we can see this is a deletion error, but here we can see this method doesn't have this kind of deletion errors. I just said, we are trying to use phase iterative phase reconstruction to improve the phase part. So another work we are trying to do is to do the time domain, which is we use the signal itself as input, then the output is the separate signal. So we use the encoder and decoder to replace the short-time Fourier transform and the invert short-time Fourier transform. Then this network-based encoder and decoder doesn't decompose the signals into phase and magnitude. So this kind of work doesn't have phase problems. Then it means without the phase problem, this method will improve. Will achieve better performance. So most of the time domain speed separation systems adopts this kind of framework using the encoder to encode the time domain signals into the feature implementation. Then use a separator to explain masks. Then use the mask to filter as a capture the feature implementations. Then finally use the decoder to reconstruct the signals. So the recently many of the works have been done in the time domain speed separation. They mostly try to improve the network structures. For example, use BRSTMs, temporal convolutions, dual paths, or the multi-head attention. Also, they try to use the two stages, which is in the first stage, they try to use a good speech encode and decode. Then after that, they fix the encode and decode to learn the separator. Also, is another is using the fixed permutation to assign the labels to calculate the errors. Also, the hybrid systems, which combines the information from frequency domain and the time domain. Also, the multiple iterations, which means we do the separation first, then we use the separated output together with the original mixture, then do the second round separation. then we can do several round iterations. So then we can further improve the performance. Also, the pre-training for robustness, because in the time domain method, the speech encoder mainly learns from the data. Then the data distribution may be affect the performance. For example, if we train in one kind of data set, and then we test on a different data distribution of real world signals, then the performance may be the performance becomes worse. So we can use the pre-training or unsupervised training or self-supervised training using a lot of real-world data to initialize the models. Then we can improve the robustness. But also another work is to try to generalize the model trained in one language to other languages. As I just said, most of the works are adopted the encoder, separate, and decode frameworks. So they replace the network structures, for example, the bidirectional STM or stacked temporal convolution networks. In the second stage, in the two-stage method, they try to use train or encode and decode first, which means they use the clean speech together with the mixture speech as input. Then they use the softmax to get the ideal masks. Then they train the encoder and decode. After they will train the encoder and decoder will train, then we fix them. Then we train the separator. After the whole network is trained, then we can have our final speech separation system. Also, we can try to fine-tuning the encode and decode again. So another work is to do the label assignment. In the permutation invariant training, as we know, we calculate the errors across all the permutations. So we find the permutation with minimal errors. But sometimes the permutation assignment for the same input may be different from epoch to epoch. So it means in this training epoch, the assignment output 1 is to reference 1, output 2 is to reference 2. But in the next epoch, the output 1 maybe go to the output the reference 2. The output 2 maybe goes to the reference 1. So the assignment changes. So it's not good for the training part. So this work try to study 4 different kinds of label assignment, which is based on the energy-based label assignment. For example, for the output 1, we always output the speakers with higher energy. The second one is the speaker with lower energy. So we fixed of this kind of labels. Another one is a speaker unbanding based one. Actually, we calculate the estimated speech and the reference speech to use the speaker unbanding to do the label assignment. Another one is a fixed label assignment using the permutation from the PIT. For example, we train the PIT with 100 epochs. After that, we use the permutations for all the training data, and we fix them. Then we retrain the system. Another one is we interrupt the PIT with the inserted section of fixed level training, which is we train the PIT first, then we use 100 epochs of the label assignment to retrain the network. After that, then we use the PIT again to further train the network so we can achieve better performance. So this work is try to combine the information from different domains, for example, in frequency domain and the time domain. So they just combine the features together to do the mask estimation, then estimate the masks in both time domain and fixed domain, and then to train the network. So the performance can be improved by combining these two kind of different informations. Previously, we say we using the bidirectional RSTM or temporal stacked temporal convolution networks. It means we want to capture the sequential information. But if our input is very long, the sequential information may be not good captured by bidirectional RSTM or stacked TCN. So some of those works try to use the dual path, which means we use intro and inter module to capture the local local information and the global information. So how they do this is they first do the segmentation by the segment the long sequence into short one by 15% overlap. So after they get this kind of segments, then can form a 3D matrix. Then with that we can do the inter first. We do the inter feature learning along the temporal dimension. After that, we permutate, which is a transposer. Then we learn across the segment, which is we capture the global information. After we learn this kind of features for each speaker, then we do the overlap and add to reconstruct the time dimension loss. So for this dual path networks, the DPRNA actually use the bidirectional RNA in the intro part and in the inter part. So the gated one means they use a gated mask after this to improve the performance of DPRNA. So the DPNet, which is a dual path transform, they replace the bidirectional RNA with transformers. The GALR, which is they do the local information capture with bidirectional RSTM. The global one, they use the multi-head attention. So the standard glasses, they try to use the unit structure. Actually, in the unit structure, they in the each layer of the unit, they use the local one, the global one, which is the local one uses RN, and then the global one uses self-attention. The self-former is similar to the DPNet. They use the transformers in the interpart and the interpart. This SAFE-IT, which is the one I mentioned previously to do the separation multi-run. For example, we evaluate the multi-run of DPRN, multi-run of self-former. Then it shows if we do the multi-run separation, the performance can be further improved. As I previously said, the time domain has a problem is we cannot generalize to unseen or different data distributions because we train on a database. Then all of the networks are learned from this database. Then it may not generalize to other database. Also the real-world applications. So actually here we propose a system for speech enhancement, of time domain speech enhancement. We have we use matrix, the noisy speech and the clean speech. Actually, they are not paired. So for the noisy speech, we can have a lot of noisy speech in the real applications. For the clean speech, we can record it in the silence rooms. So this X and the Y is not required to be a pair. So in the supervised, in all of the previous works, we do the supervised learning. We need to have the paired data, which is the input and the clean reference. They are paired. So in this unsupervised pre-training, we don't need to be the data to be paired. So this case is evaluated on the speech enhancement. We estimate the noise part and the speech part. So we use the discriminator and the reconstruction loss to pre-train this network. So this can be extended to the speech separation, which is we have separated for each speaker. Then we can also use this kind of loss. So in the second stage, we do the mixture training. For the mixture training, we still use a lot of mixture noisy data without labels. Also, we have a small amount of data with paired data, so we can further improve the performance. Because this data is also learned from the real-world applications. For example, the noisy the unpaired noisy data. So this one can generalize the real to the real applications. Also, we have the mixed IT. For the supervised preliminary training, we have two sources, which each source is clean. Then we have the separation. Then we combine them, or we use one of them to calculate the loss. For this unsupervised one, it means we have mixtures. We try to combine them together to get a mixture of mixtures. Then we separate individual of the speakers. Then we do the remix. So we have a lot of implementations. We do remix. Then we calculate the loss between the mixture and the remixed signals. Then we can do this self-supervised training. Also, there are some other works to do the pre-training. For example, they use speech enhancement system as initialized to train the network. Actually, this work is not mentioned and not listed here. So here is the performance of the works I talked about. So this part mostly are the frequency domain method, and this part are mostly the time domain method. So we can see the time domain method achieves better performances than the frequency domain. So also this deep CASA is frequency domain by 2 stages. So actually this some of them is try to improve the network structures. If this kind of network structures is used in the frequency domain method, maybe the frequency domain the performance also improve. So we also conduct another work which is try to generalize the models from one language to other languages. So we have the global phone database, which is 2 languages, more than 2,000 speakers. So we use 5 languages to train an individual systems. Then we use the rest 17 to as an evaluation. So we also evaluate on the trained network. So for each, for the trained system, if we train individual system with the single language, then it only can work well on the same languages. Sometimes they can work well on the part of language, similar languages, but they cannot. In most of the cases, they cannot work well in other languages. But if we combine several languages together, then the performance can be significantly improved each of these languages. Then for these unseen the 17 languages, they can also achieve the best performance. So yeah, I want to say, so if we want to design a general system to handle different case of scenarios. For example, some speakers can speak binary languages or trig language. So we can use this kind of language augmentation training, which is combine several different language training system to generalize real to unseen languages. Another problem in speech separation we want to solve is unknown number of speakers. So we say during training we know how many speakers in the mixture because we are the data is simulated. We know how many species in each mixture we have added. So, but during the inference for the real applications, we cannot know the number of speakers. So what we can do is we can do the iterative separation. In each stage, we only output the speech of one speaker. So we have the rest masks. So this residual mask and the input string is used to do the second round estimation. So we do the several round, and then we can get the separation of each speaker. Actually, we have two different kind of stop threshold. The first one is we can set a threshold to the mask. If the mask is all zero, it means there is no rest speaker need to be separated, then we can stop the iteration. Another one is we can use a threshold to set the number of iterations we conducted. For example, we only want to get 3 speaks, then we do 3 iterations. Because most of the case, for example, in the conference, when speakers overlap, most of the case are 2 speaker separation. Some small portion are the 3 speakers. So, for example, we can say we do 5 round iterations, then it may be enough for the case we want to get the speakers of all the overlap part. Then we can do some threshold to see how many speech, how many output of silence. And okay, maybe we'll have a break. Then after that, we have the second part. So if you have any question, you can type in the chat or you can raise your hand. Then we can talk about.